Welcome to this quiet channel, where we take our time with the strangest corners of everything that exists. There are places out in the dark so far beyond ordinary experience that the mind simply slides off them. A star so packed and dense that a single spoonful of its material would crush a mountain flat beneath its weight. Magnetic fields so violent they unravel the very atoms of ordinary matter from a distance measured in thousands of kilometers. Edges in the fabric of space from which not even a beam of light has ever found its way back out. A cloud of gas so thoroughly drained of heat that it sits a single degree above the coldest temperature physics allows. These are not imagined places or theoretical constructs borrowed from science fiction. They are real, they are out there, and they're turning quietly in the dark right now as you rest. Tonight we visit the most extreme of them, moving carefully from one to the next without hurry or alarm. If you find this kind of slow exploration worth your time, a like or a subscription helps other quiet minds find their way here. Thank you for being in this space tonight, and for choosing to spend a few hours this way. For the next couple of hours, none of what we visit can reach you, and that matters more than it might first seem. Every place on this tour is separated from you by distances so vast they become a kind of shelter all their own. The forces we will stand beside in our minds are indifferent, ancient, and entirely unaware that anything small and warm exists here on this world. So there's nothing to brace against, nothing to prepare for, nothing to carry forward into your night. Let the awareness of that distance settle into your shoulders the way warmth settles into tired muscles after a long day finally ends. Let your jaw loosen just slightly, and let the breath find its own slow rhythm without your help. The day you carried here has already done its work, and it does not need you anymore tonight. You are allowed to put it down completely, the way you might set a heavy bag on the floor and simply walk away from it. The universe will hold your attention gently from here, and you will not need to grip anything at all. Let's begin where the extremes are most complete, on a world made entirely of the hardest thing nature knows how to build. There's a kind of object in the deep sky that represents matter pushed past every boundary our everyday world can suggest. It forms when a massive star, after millions of years of burning, finally exhausts the fuel that held it open against its own tremendous weight. The outer layers collapse inward in a fraction of a second, and the core is squeezed so violently that ordinary matter simply ceases to be what it was. Protons and electrons are crushed together under pressure no laboratory has ever approached, until almost nothing remains but neutrons packed side by side with no space left between them. The result is a sphere roughly 20 kilometers across, no wider than a single large city laid edge to edge. And yet that modest sphere holds more total material than our entire sun contains across its vast interior. This is not a metaphor or an approximation borrowed from an older era of astronomy. It is the measured, confirmed reality of objects we have been studying for decades. The densest things we can directly observe anywhere in the known cosmos are not dramatic clouds or exotic distant phenomena. They are these small, quiet, almost featureless spheres sitting alone in the dark. The numbers attached to a neutron star resist every attempt to make them feel real, and that resistance is itself worth noticing. A single cube of neutron star matter the size of a sugar cube, small enough to rest between two fingers, would weigh approximately 1 billion tons on the surface of the Earth. That is the weight of a mountain, compressed into something you could theoretically hold in the palm of your hand. The matter is bound so tightly that the rules governing every physical object you have ever touched simply stop applying at those densities. Nothing on Earth is built this way. Nothing ever could be built this way, and nothing in our experience offers any true comparison. The gravity at the surface of a neutron star runs roughly 100 billion times stronger than the pull you feel right now holding you against the ground. An object released from a height of just 1 meter above that surface would strike it traveling at thousands of kilometers per second. The crust of a neutron star is thought to be billions of times stronger than the finest steel ever forged by human hands. And yet even that extraordinary rigidity is no match for the gravity pressing down on it from every direction at once. The mountains on a neutron star deserve a moment of particular attention because they overturn every intuition about scale. On Earth, a mountain range rises kilometers into the sky and dominates entire landscapes visible from orbit. On a neutron star, the crust is strong enough to support surface features, but the gravity is so crushing that the tallest peak the entire planet can sustain rises only a few millimeters above the surrounding ground. An entire mountain, by the standards of that world, stands no higher than a coin balanced on its edge. This makes the neutron star surface the flattest, most level terrain anywhere in the observable universe, smoother in proportional terms than any ball bearing ever polished in a human workshop. There is something unexpectedly peaceful in that image, a world ironed perfectly smooth by forces too large to argue with. The star does not resist its own gravity or struggle against the crushing weight above its core. It simply yields to the math completely, and the result is a kind of absolute levelness that has no equal anywhere in nature. A place where nothing stands tall, nothing juts upward, and nothing reaches toward anything else. Many neutron stars rotate at speeds that challenge every instinct about how large objects behave in space. A young one can spin tens or even hundreds of complete rotations every single second, carrying all of that compressed mass around in an unbroken rhythm. The fastest confirmed neutron star rotates approximately 700 times in a single second, and its surface moves at a meaningful fraction of the speed of light as it does. Some of these spinning remnants sweep narrow beams of radio energy across the sky like the rotating beam of a distant lighthouse, regular and patient and precise. When one of those beams happens to sweep across the line of sight from Earth, we receive a brief pulse once per rotation, arriving with clockwork reliability. The rhythm is so dependable that certain neutron stars rank among the most accurate natural timekeepers anywhere in the universe, outperforming many clocks built by human hands across spans of years. Beneath the crust, the interior may be occupied by a frictionless flowing state of matter called a superfluid, moving without resistance through the deeper layers. Closer to the inner edge of the crust, matter may be squeezed into unusual elongated shapes that physicists have nicknamed nuclear pasta, tubes and sheets of nuclear material with no equivalent on Earth. These layers can never be seen directly, and we know them only through careful reasoning and the faint signals the stars send outward. It is knowledge built from whispers. When a neutron star is first born from the collapse of its parent, its surface blazes at roughly 1 million degrees, pouring out light in wavelengths far beyond what any human eye can register. Over long ages measured not in years, but in eons, it gradually sheds that heat into the surrounding dark, cooling with a patience that makes geological time feel rushed by comparison. It has nowhere to be, no deadline is working toward, no cycle of any kind that demands anything from it. It simply turns and cools, turning and cooling, across timescales that reduce an entire human civilization to something shorter than a single heartbeat. And here, early in our tour, something shifts in the emotional texture of the journey. For all the crushing weight and unimaginable density, the neutron star is also one of the most serene objects in existence. It is smooth across its entire surface, balanced perfectly against its own gravity, spinning in an unbroken rhythm that has continued since long before the sun first caught fire. It threatens nothing. It reaches toward nothing. It simply persists far away in the dark, doing what it has always done with complete indifference to everything around it. The way we find neutron stars is worth holding in mind because it adds something quietly beautiful to the picture. Many of them announce themselves not through brightness or heat, but through rhythm, a steady patient ticking that arrives from a fixed point in the sky. When the first such regular pulse was detected by astronomers, the signal was so precise and so regular that for a brief period it seemed almost too structured to be natural. Those who first recorded it gave it a half-joking private designation that acknowledged the strange possibility that something deliberate might be behind it. The true explanation turned out to be stranger and more satisfying than any signal ever could have been. A dead star, spinning in the dark, sweeping its beam across space with the faithfulness of a mechanism that has never been serviced and never needs to be. What had seemed at first like a message was instead the simplest thing imaginable, a small, dense object, patiently announcing its rotation across the light years. Thousands of these objects are now known throughout the galaxy, each keeping its own steady time, a scattering of faithful rhythms distributed across the dark like the ticking of 10,000 clocks left running in empty rooms. The balance that allows a neutron star to exist at all is finally held, and it is worth pausing on that briefly. As the core of a dying star collapses, the neutrons packed into the remnant resist being compressed any further, and that resistance is precisely what holds the star against its own gravity. But this support has an upper limit, somewhere in the range of 2 to 3 times the mass of our Sun. If the remnant exceeds that threshold, even the densest packing of neutrons cannot hold, and the collapse continues through a boundary from which there is no return. A neutron star sits balanced at one of the most precise thresholds in all of nature, heavy enough to crush ordinary matter completely out of existence, and just light enough to stop short of crossing into something from which no information ever escapes. It holds that balance without effort and without strain for billions of years at a time, steady and quiet at the edge between two kinds of impossible. There is something almost restful in the idea of an object so perfectly placed that neither its own weight nor the resistance of its matter can tip it one way or the other. So we let the neutron star rest where it sits, the densest stable ground the universe contains, smooth and quiet and impossibly remote. It has been spinning there since before our world gathered from its cloud of dust and gas, and it will continue spinning long after the last traces of everything we have ever built have dissolved back into the dark. It asks nothing of the night, threatens nothing we love, and offers nothing except its patient presence and its faithful ticking, carried across the light years to instruments we built because we were curious. That curiosity connects us to it across a distance our bodies could never cross, and there is something warming in that thread. The most extreme ground in the universe is also, in its own way, a kind of company. And from this dense and level place, we turn now to a close cousin of a neutron star, an object whose extremity lives not in its weight, but in the invisible force that surrounds and saturates it entirely. Among all the neutron stars in the galaxy, there's a rarer kind, and it carries the most powerful magnetic field ever found anywhere in the known universe. That rarer kind carries a magnetic field so extreme it belongs in a category entirely separate from anything else. The word magnetic covers a wide range of phenomena in our ordinary experience, from refrigerator ornaments to hospital scanners. But the field surrounding a magnetar sits so far beyond those familiar examples that the same word feels almost dishonest applied to both. Earth itself is a magnet, gently enough that a small suspended needle will drift toward its northern pole with patient reliability. A magnetar's field exceeds that quiet terrestrial pull by roughly 1,000 trillion times, a number the mind cannot picture in any honest way. It is worth sitting with that ratio for a moment before trying to understand what it actually does to the space around it. The field is not merely stronger in the way a larger engine is stronger than a smaller one. It is stronger in a way that a hurricane is stronger than the breath that turns a page. Every intuition we carry about magnetic force has to be set aside before this object makes any sense. The field's most unsettling quality is not its strength in the abstract, but what that strength does to ordinary matter at close range. Atoms are mostly empty space organized by electrical forces into rough, spherical arrangements. Electrons drifting in clouds around small, dense nuclei. Near a magnetar, within a range of several thousand kilometers, the field distorts that familiar geometry completely. The electron clouds are no longer free to occupy their natural rounded shapes, but are stretched lengthwise into thin, elongated needles aligned along the field's direction. The chemistry that holds substances together depends entirely on those cloud shapes, on the angles and distances between atoms bonded into molecules. When the shapes are forced into something unrecognizable, the chemistry quietly dissolves, not through heat, not through impact, not through any force we associate with destruction in daily life. A body placed within that range would come apart through the silent pressure of magnetism alone, its atomic architecture rewritten without any violence that could be heard or felt arriving. From time to time, the magnetar does something that reveals just how much energy is wound into its invisible structure. The crust of a star is a rigid shell held under enormous stress by the competing demands of the field pressing outward and the gravity pressing inward from every side. Occasionally, that stress exceeds what even the strongest material in the universe can hold without moving, and the crust shifts in what physicists describe as a starquake. The field, suddenly released from its previous configuration, snaps into a new arrangement in a fraction of a second. The energy released in that adjustment pours outward as an intense burst of high-energy radiation traveling at the speed of light in every direction at once. A single such flare from a magnetar tens of thousands of light years away once carried enough energy across that enormous gulf to gently perturb the outermost edge of Earth's atmosphere. It caused no damage, left no mark, and was felt by nothing alive. It simply registered on instruments, a faint touch from something unimaginably remote. That particular detail is worth dwelling on because it reframes the whole picture in a useful way. The event that nudged our atmosphere originated from a star so distant that its light takes tens of thousands of years simply to make the crossing. By the time that burst arrived here, it had spread across a sphere of space so large that our entire solar system occupied a vanishingly small patch of its surface. What landed on our instruments was a whisper of a whisper, the faint remainder of something that had spent itself almost entirely into the dark long before reaching anything. The original flare, at the moment of its release, briefly outshone every other star in the Milky Way combined, pouring more energy into a fraction of a second than our sun will produce across many thousands of years. And yet the portion that arrived here was gentle enough that nothing noticed except the most sensitive instruments we have ever built. Distance transformed an event of nearly incomprehensible violence into something quieter than a breath of wind on a still afternoon. The origin of the magnetar's extraordinary field lies in the circumstances of its birth, and that origin is itself a story of extreme physics becoming extreme structure. When a giant star collapses and the newborn remnant is both spinning very rapidly and churning vigorously through its interior, a dynamo effect takes hold at a scale nature rarely permits. The churning motion winds the magnetic field up with each rotation the way a coil of wire wound around a core builds a field each time current passes through it. In ordinary neutron stars, this process produces fields already far beyond anything Earth can match. In the rare cases where the rotation is fast enough and the internal churning vigorous enough, the winding continues past all ordinary limits, locking a reservoir of energy into the field itself that the star cannot easily release. That stored energy is what makes the magnetar restless, what keeps the crust under strain, and what drives the occasional sudden adjustments that send light racing outward across the galaxy. A magnetar is young by cosmic standards, typically only thousands of years removed from the collapse that created it. But youth here does not mean weakness. It means the field has not yet had time to decay and is something quieter. Over those same thousands of years, the field does gradually weaken, leaking its stored energy into space as heat and radiation at a slow and steady rate. As it weakens, the crust relaxes, the starquakes grow less frequent, and the sudden flares become smaller and rarer. The magnetar is slowly settling toward a calmer existence, draining its reserves the way a charged battery slowly loses its potential in the dark. Eventually, it will arrive at something resembling an ordinary neutron star, its great field spent, its crust at peace, its rhythm quieted to a patient ticking. There are only a few dozen confirmed magnetars known to us across the entire galaxy, each one a brief and uncommon visitor, burning through its fierce inheritance before fading toward stillness. It helps to hold the geometry of the situation clearly in mind, because the geometry is what makes the magnetar harmless from our position. The nearest known magnetars lie thousands of light years from Earth, a distance so vast that the strongest magnetic field in the universe is reduced by the time it reaches us to something instruments can barely register. The field weakens with distance the same way all fields do, spreading across a larger and larger sphere as it radiates outward from its source. By the time any signal from even the most energetic magnetar flare completes the journey across thousands of light years, it has thinned across a surface area so enormous that its strength per unit is negligible. We are not merely far from these objects in the sense of being inconvenienced by the distance. We are sheltered by it in a way that is close to absolute. The field that could dissolve an atom at close range arrives here, without the strength to deflect a single compass needle by any measurable amount. There's a thought experiment that circulates in discussions of magnetars, and it captures their nature more vividly than any number can. If a magnetar were somehow brought to the distance of the moon, which is itself the closest any large astronomical object ever comes to us, its field would reach across that gap and affect every magnetic strip on every card on the surface of the Earth. Every device relying on any magnetic component would feel its presence. This would happen silently, without light or heat or any detectable arrival. Simply a field restructuring things at a distance, because that is what a field of that strength does through empty space. The thought experiment is useful not because the scenario is possible, but because it gives the field a human scale that makes its nature tangible in a way the raw numbers cannot. The nearest magnetars lie not at the distance of the moon, but at distances millions of times greater than that, and the thought experiment simply vanishes into that context like a candle held up against the sun. For all its violence and its restlessness, there is a quality to the magnetar that belongs naturally in the same meditative space as the neutron star we visited before it. Its power is entirely invisible and entirely silent, a force that works by rearranging things at the level of their deepest structure without making a sound. It sits alone in a far part of the galaxy, most likely in a region with no close neighbors, spending its fierce inheritance into the dark at a rate no living thing will ever notice. It does not hunt. It does not move toward warmth. It does not reach out across its thousands of light years of separation, looking for anything to unmake. It simply is, turning in the dark with a field that slowly weakens around it, growing quieter with each passing age, working its way patiently toward the calmer existence that waits at the end of its brief and intense youth. The most powerful magnet the universe will ever build is also one of its most solitary objects, alone and fading in the long silence between the stars. And so the magnetar settles into the same quality of distance and indifference that the neutron star carries, extreme beyond imagination and unreachable in any practical sense that touches anything we love. Its great field is winding down across thousands of years towards stillness, its flares growing rarer, its crust relaxing by degrees into something more like peace. We will never stand anywhere near it, and nothing about it will ever come near us. It exists as an object of contemplation rather than concern, a fact about the universe that is simply true, the way a deep canyon is simply true, requiring nothing from the person who learns it exists. From these two objects built from the compressed remnants of dead stars, both extreme in their own quiet ways, we turn now towards something that has not yet died, a star still burning through its final ages, so enormous that the word large no longer feels adequate to carry what it means. Among the neutron stars that turn in the dark, there exists a rarer and more restless kind, carrying something the universe rarely permits. Its extremity lives not in the density of its matter, but in the invisible architecture of force surrounding it completely. Where a neutron star is a study in weight and compression, this object is a study in field, in the kind of force that reaches outward through empty space and changes what it touches. It is called a magnetar, and every other magnet that has ever existed anywhere in human experience becomes trivial beside it. The Earth itself is a magnet, patient and gentle, turning compass needles toward north with a force you could overcome with a single finger. A magnetar's field exceeds that terrestrial pull by a factor of roughly 1,000 trillion, a ratio so disproportionate it stops behaving like a number at all. It becomes instead a kind of fact about a different order of things, a different category of what nature allows. Before considering what such a field does to matter, it helps simply to acknowledge that the same word covers both objects only by convention. The field around a hospital scanner is strong enough to pull keys across a room. What surrounds a magnetar is something the word magnetic was never designed to carry. The field's most striking quality is not its strength measured in isolation, but the work that strength performs on ordinary matter at close range. Atoms are not solid objects, but arrangements of mostly empty space organized by electrical force into rough spherical territories. Electrons occupy cloud-like regions around their nuclei, and the geometry of those regions determines everything about how atoms bond and what substances form from their combinations. Near a magnetar, within a distance of several thousand kilometers, the field imposes itself on those geometries with complete authority. The electron clouds can no longer hold their natural rounded forms, but are drawn out lengthwise into narrow rods aligned along the field's direction, like soft shapes pressed through a narrow mold. When the cloud geometry changes, the chemistry built upon it dissolves quietly and without announcement. No heat is required, no collision, no incoming projectile carrying kinetic force. The bonds that hold matter together simply loosen and rearrange, restructured by an invisible pressure arriving from across empty space. A body placed within that range would not be struck or burned or crushed in any familiar sense. It would be quietly taken apart at the level of its smallest architecture, unmade by silence. From time to time, the magnetar reveals the full scale of its stored energy in a single sudden event, and those moments carry numbers that resist ordinary language. The crust of a magnetar is a rigid shell held under competing pressures, the field pushing outward and gravity pressing inward from every side, and occasionally that tension exceeds what even the densest known material can hold without yielding. The crust shifts in a brief and violent adjustment, a starquake, and as the field snaps into its new configuration, the energy release pours outward as a burst of high-energy light traveling in every direction at once. A single great flare of this kind can briefly pour out more light than every other star in the Milky Way combined, every one of those hundreds of billions of stars outshone for a moment by one small object adjusting its posture. One such burst originated from a magnetar tens of thousands of light years distant, and still carried enough energy to register a faint disturbance in the uppermost edge of Earth's atmosphere. It caused no damage, disturbed nothing alive, and was felt only by instruments designed specifically to notice such things. A tremor from something that far away, that gentle by the time it arrived, yet detectable at all. That detail deserves more attention than it usually receives, because it reframes what the magnetar actually is from the perspective of anything standing safely distant. The flare that nudged our atmosphere had already crossed a gulf so wide that its energy was spread across a sphere of space measuring tens of thousands of light years in radius. The original event, compressed into a fraction of a second, released more energy than our sun will produce across many thousands of years. What arrived here was a remnant so diluted by the crossing that sensitive instruments could barely confirm it existed. Distance performed the same transformation it performs on every extreme thing we visit on this tour, taking something that would be lethal at the source and reducing it by the simple geometry of spreading across space into something no more threatening than a breath of wind on a calm afternoon. The magnetar did not become less extreme by that journey. Its nature at the source was unchanged, fierce and restructuring and complete. Only what reached us changed, and what reached us was a whisper so faint it required our most patient instruments simply to hear. The origin of the field itself lies in the circumstances of the magnetar's birth, in the brief and violent window when a collapsing star first becomes something new. When the right combination of rapid rotation and vigorous interior churning coincides in a newborn neutron star, a dynamo process takes hold at a scale ordinary physics does not prepare you for. The internal motion wins the magnetic field with each rotation, the way turns of wire around an iron core build a field in a simple electromagnet. Except the core here is nuclear matter, and the current is the churning of the densest fluid the universe makes. In ordinary neutron stars, this process produces fields already far beyond terrestrial comparison. In the rare cases where early rotation is fast enough and the internal turbulence vigorous enough, the winding continues past every ordinary ceiling, locking a reservoir of energy into the field that cannot be quickly released. That reservoir is the magnetar's inheritance from its birth, the stored potential that keeps its crust under strain and drives its occasional sudden adjustments across thousands of years of restless life. A magnetar is young in the only sense that matters for an object of its kind, typically only a few thousand years removed from the collapse that made it, which is a brief childhood by the standards of stellar remnants that endure for billions of years. But that youth carries its full intensity rather than its innocence, the field at its strongest, and the crust under its greatest strain precisely in these early ages. Over those thousands of years, the field gradually drains its stored energy into space as heat and radiation at a slow, steady rate that the star cannot quicken or slow by any internal choice. The crust relaxes by degrees as the pressure eases. The starquakes become less frequent. The flares grow smaller and more widely spaced, and the magnetar moves along a slow gradient toward the calmer existence of an ordinary neutron star waiting at the end of its brief, fierce youth. There are only a few dozen confirmed magnetars known throughout the galaxy, each one a passing phase rather than a permanent condition, burning through its inheritance before settling into the patient quiet that follows. The strongest magnets the universe will ever build are also among the shortest lived, flaring for a cosmological instant before fading into the long silence. The geometry of the situation is what transforms all of this from a source of unease into something closer to a fact about a distant place, interesting and undisturbing in equal measure. The nearest magnetars lie thousands of light years from Earth, a separation so vast that the inverse square law of how fields weaken with distance reduces even a magnetar's extraordinary field to something instruments can barely register at this range. The field that would dissolve an atom's architecture within a few thousand kilometers of the source spreads outward across a sphere that grows larger with every light year of the crossing. By the time any portion of that field reaches us after traversing thousands of light years, it is thinned across a surface area so enormous that its density per unit has become negligible. We are not merely distant from these objects in the way a traveler is distant from a city they have no plans to visit. We are sheltered by the physics of how fields propagate through space, protected by mathematics as reliably as by any physical barrier that has ever existed. There is a thought experiment sometimes offered to give the magnetar's reach a human scale, and it is worth considering carefully because it clarifies the nature of the field rather than inflating the danger. If a magnetar were somehow positioned at the distance of the moon, roughly 250,000 miles from Earth, its field would reach across that gap and affect every magnetically sensitive surface on the planet. Cards with magnetic strips, devices relying on magnetic components, compass needles in every pocket and on every wall, all would feel the field's presence, silently and simultaneously, without any light or heat or sound announcing the arrival of that influence. The scenario is not a prediction or a warning, but a calibration, a way of understanding what a field that strong actually means in terms of reach and effect. The nearest magnetars do not sit at the distance of the moon. They sit millions of times farther away than that, and the thought experiment dissolved entirely into the scale of the separation, leaving only the fact of an extraordinary object doing something extraordinary in a very remote part of the galaxy. For all its restlessness, there is a quality to the magnetar that finds its natural place in the same quiet register as the dense and level world we visited before it. Its power operates entirely through an invisible field, through silence rather than sound, through restructuring rather than impact, through a force that works without announcing itself to any sense that could perceive an approach. It spends its fierce inheritance alone in a distant part of the galaxy, most likely without close neighbors or any nearby matter dense enough to feel the full weight of its presence. It does not move toward warmth or light or any concentration of ordinary matter with any kind of intention. It simply exists in a single location, turning as it has since its birth, its field settling by degrees toward the calmer geometry that will eventually replace it. The most powerful magnetic object the universe constructs is also among the most solitary, and that solitude is not incidental to its nature, but a feature of where objects like this tend to form and how they tend to age. Something this extreme, it seems, tends to be left very much alone. The magnetar will go on fading towards stillness across the thousands of years ahead of it, its crust growing quieter, its great field thinning toward the baseline of an ordinary neutron star, until at last it joins the patient company of spinning remnants that turn in the dark without urgency or announcement. We observe it from a distance that renders its extremity entirely academic, a fact about the universe that requires nothing from us in return except the willingness to understand what we are told by careful instruments and patient reasoning. And from this solitary and fading object, built from the remnants of a star that lived and died before our world began, we turn now toward a star that has not yet died, one that is living out its final ages in a very different kind of extreme. It is not small and dense and fierce. It is the opposite of all those things, an object so swollen and so vast that the very idea of its surface becomes difficult to locate at all, and the inner planets of an entire solar system would sit deep within its glowing outer layers. The giant that lived out its final ages in swollen silence has now reached the moment it cannot negotiate past. At the center of that enormous star, the iron core has stopped doing the one thing that mattered, releasing energy through fusion. The fire that held billions of tons of stellar mass from collapsing simply goes out, the way a held breath finally has to be released. Gravity, which the star spent its entire existence resisting, wins completely in less than a second. The core falls inward at a fraction of the speed of light, reaching densities that briefly rival the neutron star we visited at the very beginning of this tour. Then the neutrons resist being squeezed any further, and the collapsing core rebounds outward in a shock of almost unimaginable force. The outer layers of the star, still falling inward behind the core, meet that rising shock and are thrown outward into space at thousands of kilometers per second. In those first few seconds, the dying star releases more energy than our sun will produce across its entire 10 billion year existence. Most of that energy does not travel as light, but as neutrinos, the nearly weightless particles streaming outward through the rest of the star before the visible blast has even organized itself. Neutrinos are worth a moment of slow attention because they reveal something strange about where the real energy goes. They are particles so reluctant to interact with ordinary matter that streams of them pass through entire planets without touching a single atom they encounter. Right now, as you rest, countless neutrinos from our sun are traveling through your body from one side to the other, and you will never feel a single one of them. In a collapsing stellar core, they're produced in numbers that make the sun's output seem modest, pouring outward in a flood so dense that even they, for a brief moment, struggle to escape the collapsing interior. They carry away the overwhelming majority of the supernova's energy, racing outward through the dying star before the shock wave has begun its outward journey through the outer layers. By the time the visible explosion lights up and begins to brighten, the neutrinos are already long gone, spreading across space in every direction at nearly the speed of light. We detected a handful of them from a supernova in a nearby companion galaxy decades ago, arriving at our instruments a few hours before the visible light became bright enough to notice. That tiny advance signal confirmed what the theory had long predicted about where the real energy of stellar death actually travels. The shock wave that follows moves through the outer layers of the star at speeds between 10,000 and 30,000 kilometers every second, a few percent of the speed of light. At the temperatures produced inside that blast, which climb into the billions of degrees, the lighter elements of the dying star are forged rapidly into heavier ones by the same kind of nuclear fusion that powers ordinary stars, only at a pace and intensity that no living star ever reaches. The supernova is not only an ending in this sense, but a forge, a brief and violent kitchen in which elements that ordinary stellar burning cannot produce are assembled and then scattered outward into the surrounding space. 4 weeks after the initial explosion, the expanding cloud glows across many kinds of light, sustained by the slow radioactive decay of freshly made elements within the spreading material. Astronomers watching from a safe distance can read the brightness curve as it rises and falls, extracting from it a detailed record of what kind of star died and how. The whole biography of a stellar life compressed into the shape of a single fading arc of light. What starts as the most violent event in nature leaves behind a slowly dimming cloud and a set of measurements that tell the whole story. Here the tour turns towards something more personal than any of the extremes we have visited so far. The calcium that gives your bones their hardness was made inside a star. The iron carried in your blood, responsible for binding the oxygen each breath delivers, was forged in stellar cores and scattered by explosions very much like the one we are describing now. The oxygen itself that moves through your lungs as you rest, the element that makes this kind of slow breathing possible, was assembled inside massive stars and released into the galaxy when those stars ended. None of these materials arrived on Earth by accident or from some original supply waiting here since the beginning. They were made elsewhere in conditions far more extreme than anything this world has ever known, and they were distributed across the galaxy by the very deaths we are now contemplating at a careful distance. A supernova is the most powerful detonation nature produces, and it is also the reason small rocky worlds like this one have the ingredients to become anything at all. The violence and the gift are the same event, inseparable, each requiring the other to be what it is. It is fair to ask whether any of this could reach us in a way that mattered, and the honest answer settles the question without requiring much elaboration. A supernova would need to occur within roughly 25 to 50 light years of Earth to produce effects capable of seriously affecting the atmosphere. No star close enough to qualify is in the late stages of life that would lead to this kind of ending. The massive stars capable of producing a supernova lie far beyond that threshold, separated from us by the same enormous distances that reduce every other extreme on this tour to a distant and harmless fact. We watch their endings from comfortable remove, receiving only the light that spreads across hundreds of millions of light years before arriving here, as a point of brightness that slowly fades over weeks and months. Those brief brightenings in the historical sky were noticed by people who had no way of knowing what they were watching, new stars appearing and then slowly disappearing over the course of weeks, recorded in stone and in careful astronomical logs. They were witnessing the deaths of giant stars, the light from those endings arriving after journeys of thousands of years, bringing news of an event that had already scattered its elements into the dark long before the signal left its source. Sometimes a star does not die alone, and when two dead stars find each other after ages of patient circling, what follows belongs to a different order of extreme entirely. Many massive stars are born in pairs, two suns orbiting a shared center across their entire lives, and when both end as neutron stars, they remain bound together in a tightening spiral. The two remnants lose energy slowly, across millions of years, radiating that loss as ripples in the fabric of spacetime itself, and their orbit gradually shrinks with each passing age. The final approach, after all that patient waiting, takes only seconds. In those last moments, the two stars are circling each other hundreds of times per second, and the spacetime ripples they send outward grow strong enough to carry energy away at a significant rate. When they finally touch and merge, the collision produces conditions more extreme than the center of any living star, and in that brief furnace, something remarkable is assembled. The merger forges heavy elements that ordinary stellar fusion cannot reach, including the gold and platinum that exist anywhere in the universe. A single such collision can produce many times the mass of the entire Earth in precious metal, scattered outward into the surrounding dark. That particular fact deserves to be held gently rather than quickly moved past. The gold in any ring, in the circuitry of any device, in any coin that has ever passed between hands, was almost certainly made in the collision of two dead stars long before our sun had formed. The most extreme collision the universe can stage is also the origin of some of the quietest familiar things we touch without thinking. The ring on a finger and the merger of two neutron stars in a galaxy billions of light years away are connected by a chain of events reaching back before the Earth existed. The violence of the collision producing something that eventually became an object small enough to hold in one hand. These mergers also send out the space-time ripples we described, gravitational waves that spread across the entire universe at the speed of light. By the time they reach us after crossing distances measured in millions of light years, they stretch and squeeze the space around us by less than the width of a single proton. We have learned to detect that tremor using instruments of extraordinary sensitivity, and in doing so we added an entirely new sense to our understanding of the cosmos. The afterglow of a neutron star merger is called a kilonova, and it shines across many different kinds of light for a few days before fading, the glow sustained by the decay of all those newly forged heavy elements settling into lower energy states. It is one of the rare events we can perceive in two entirely different ways at once, as a tremor in the shape of space and as a brightening point in the sky, two independent signals arriving from the same distant event and confirming each other. Then it fades, the sky returns to its long quiet, and the freshly made elements begin their slow drift outward through the surrounding dark, eventually to be gathered again into new clouds of gas and dust, into new stars, into new worlds. The most extreme collision the universe stages is also one of its most patient events, the final meeting prepared for by millions of years of gradual approach before ending in a handful of seconds. It makes something, scatters it, and leaves behind a small dark remnant and a slowly cooling cloud. The way a fire leaves ash and warmth after the wood is entirely gone. From the collision that shakes the shape of space, we move now to the events that briefly outshine everything else the universe contains, and they're stranger than the collisions that sometimes produce them. A gamma-ray burst is not a place in the way a neutron star is a place. It is more accurately a moment, a narrow, concentrated beam of energy fired across the cosmos and then gone. The longest ones last only a few minutes. The shortest are over in less than 2 seconds. During those seconds, a single burst can pour out more energy than our sun will produce across its entire 10 billion year life, all of it focused into two narrow jets traveling at more than 99.9% of the speed of light. Some of these events come from the collapse of especially massive spinning stars directly into black holes. Others come from the kind of neutron star merger we just described, the short bursts belonging to the mergers and the longer ones to the collapsing stars. In either case, the machinery at the center produces the same result. Matter funneled into two tight beams firing outward from opposite poles of the collapsing system with an intensity nothing else in the observable universe approaches. The reason none of this is anything to carry into an ordinary night comes down entirely to geometry. A gamma-ray burst does not radiate in every direction at once the way a star radiates its warmth. Its energy is squeezed into two narrow cones, each aimed along a particular line through space, and everything outside those cones receives nothing at all from the event. For one of those cones to matter to anything on this world, it would have to be aimed almost perfectly along the line between Earth and a suitable star close enough for the beam to arrive with enough energy to affect the atmosphere, an alignment combining precise direction with adequate proximity in a way that has remained across the entire history of life on this planet effectively zero. The beams fire outward constantly across the galaxy and across the universe, and the universe in its enormous emptiness absorbs them harmlessly, far from anything living. What we receive instead is something almost serene, a brief brightening at the edge of detection, a signal from a death that happened billions of years ago, whose light only now completes its journey. The most luminous events in all of nature arrive here as the gentlest of flickers, and from those distant blades of ancient light, we turn now toward the places where light itself can no longer find a way back out. There is a boundary in the universe where the ordinary rules of departure simply cease to apply to anything. Beyond that boundary, no particle, no signal, no information of any kind has ever returned to describe what waits inside. The event horizon of a black hole is not a wall you could touch or a surface you could stand upon feeling solid ground. It is a threshold written into the geometry of space itself, a line past which the escape velocity exceeds the one speed that sets the limit for everything. For a black hole carrying the mass of our sun, that boundary spans roughly 6 kilometers across, smaller than most cities you could name. For the giant object anchoring the center of our galaxy, the same threshold stretches across 24 million kilometers, wide enough to swallow many suns within its circumference. The number changes with the mass, but the principle holds at every scale with perfect consistency. Nothing that crosses inward carries any message back out to the space it left behind. The way time behaves near this edge is one of the strangest and most counterintuitive features of the whole picture. An observer watching from a safe distance would see a falling object slow as it approached the threshold, its light stretching toward longer and redder wavelengths, its motion appearing to freeze just at the boundary. Time itself runs more slowly in the presence of steep gravity, and near a black hole the effect becomes so pronounced that the falling object seems, from outside, to hang suspended at the edge forever. It never quite arrives, viewed from that external perspective, dimming gradually into invisibility without ever visibly crossing. But the experience from inside the fall would be entirely different, and the difference matters enormously for how you picture the place. For the object actually crossing the threshold, particularly near a truly massive black hole, there would be no wall, no jolt, no sensation of any kind marking the moment of passage. The most absolute boundary in the known universe could be crossed without noticing it had been crossed at all. The common picture of a black hole as something that actively pulls the surrounding sky inward like a drain pulling water is one of the most persistent and least accurate ideas in popular astronomy. A black hole does not reach outward beyond its gravity with any special force that ordinary objects of the same mass lack. If the sun were somehow replaced by a black hole of identical mass, the Earth would not spiral inward or deviate from its present course by a single kilometer. It would continue its same yearly orbit around a center that simply no longer produced any light, warmed by nothing, circling an invisible point through the same familiar seasons. The gravity is the same because the mass is the same, and mass is all that gravity responds to regardless of how that mass is arranged. Distance from the object is the only protection that matters, and distance here is measured in light years rather than in any unit that makes a black hole seem reachable from anywhere we stand. The question of what crossing the threshold of a large black hole would actually feel like deserves its full answer, because the answer overturns nearly every dramatic image the imagination reaches for. Near a black hole whose mass is only a few times the sun, the difference in gravitational pull between a person's head and feet would be violent enough to stretch any ordinary object apart before the edge was even reached. But a black hole containing millions or billions of solar masses presents a very different situation at its boundary. The curvature there is so gradual, spread across such an enormous region, that crossing it would feel like moving through completely ordinary space. There would be no physical sensation, no moment of alarm, nothing to register on any sense that evolution ever developed for navigating a world like this one. The terror attached to this place lives entirely in the idea of it, in the knowing rather than in any experience that would actually unfold there. The boundary itself offers no drama to the one who crosses it. Eventually, over spans of time that dwarf the current age of the universe by enormous factors, even a black hole is not entirely permanent. There is a slow process by which the boundary radiates a faint trickle of energy outward, so faint it would be unmeasurable against any background radiation present today, but real nonetheless. Across those unimaginable timescales, a black hole gradually loses mass through this process, shrinking by degrees that take longer to become significant than stars take to live and die. The smallest black holes would complete this process first, the giants last of all, but the direction is the same for all of them. The most absolute objects the universe makes are, on a long enough view, temporary, quietly dissolving back into the surrounding space with a patience that puts every other slow thing in existence to shame. The edge from which nothing returns is itself, across enough time, slowly returning to the dark from which it was made. Not every black hole sits at a fixed address that a careful astronomer can study across years of steady observation. Some of them wander. They drift through the spaces between the stars alone and dark, carrying no light of their own, tracing long, slow paths across the galaxy that no instrument watches because there is almost nothing to watch for. A wandering black hole announces its presence only when something else happens to pass almost directly behind it along the line of sight from Earth, and the gravity bends that background light into a brief brightening that careful instruments can register. One such detection, painstaking and requiring years of follow-up observation to confirm, revealed a lone black hole drifting through the galaxy, betrayed by nothing except the gentle warping of light from a more distant star. The galaxy's long history of massive stars living and dying has populated the space between the stars with an estimated 100 million such wandering remnants, most of them dark and untracked, moving through an ocean of distance too vast for any of them to threaten anything they pass. At the center of the Milky Way, where the galaxy gathers its greatest density of stars, the largest black hole in our neighborhood sits at the middle of a remarkable crowd. It holds roughly 4 million times the mass of the Sun within a region smaller than the orbit of Mercury around our own star. The stars nearest to it move in ways that reveal the unseen mass at their center as clearly as a weight reveals itself by bending a stretch cloth downward beneath it. The closest of those stars race around the black hole at thousands of kilometers per second, completing full orbits in just a few years where our own sun needs hundreds of millions of years for a single circuit around the galaxy. The density of stars near the galactic center is roughly 1 million times greater than it is out here in the quiet suburbs where our sun happens to sit. From a world near that center, the night sky would never fully darken because there would always be enough close stars in every direction to hold a steady glow across the whole dome overhead. From the galactic center, we follow the idea of a feeding black hole outward into the early universe, to the era when the largest black holes were consuming vast amounts of gas and becoming the brightest steady objects the cosmos has ever produced. A quasar forms when a supermassive black hole has an abundant supply of surrounding gas to draw inward. That gas does not fall straight through, but gathers into a spinning disk that heats under the pressure and friction of its own inward crowding to temperatures reaching hundreds of thousands of degrees, even into the millions near the inner edge. The disk blazes across many kinds of light simultaneously, and the brightest of these objects pour out the luminous equivalent of 1 trillion suns from a region no larger than our solar system. A single feeding black hole, in a space we might otherwise consider small, outshines the entire surrounding galaxy of hundreds of billions of ordinary stars by a comfortable margin. The coldest and emptiest places the universe contains sit at the opposite extreme from all of this heat and crowding, and they belong on this tour as fully as any supernova or magnetar does. Temperature is ultimately a measure of how quickly the particles of matter are moving, and the coldest anything can be is the state where that motion has nearly stopped. One particular cloud of gas, streaming outward from a dying star and expanding so rapidly that it is chilled below the faint background warmth that fills all of space, sits approximately 1 degree above the absolute lowest temperature physics permits. That background warmth, a remnant of the heat of the early universe that has been cooling and thinning across billions of years of expansion, sets a natural floor near 3 degrees above absolute zero. The cloud is colder than that floor, the coldest natural place we have identified anywhere in the known universe, quieter and stiller than the ancient warmth that surrounds it on all sides. Between the galaxies lie the great voids, enormous rounded regions of space hundreds of millions of light years across, where almost nothing is gathered, where the cosmic web of filaments and clusters simply gives way to an immense and patient openness. The largest known void stretches roughly 330 million light-years from one side to the other, a volume so wide that light crossing it takes longer to complete the journey than life has existed on this planet. Standing at the center of such a void, if it were somehow possible, you would look outward in every direction and find the same thing. A nearly empty dark, with only the faintest scattered smudges of very distant galaxies marking the edges of the opening. No band of a home galaxy across the sky, no crowd of nearby stars, nothing close or bright or familiar, only the quiet and complete openness of the most undisturbed place creation contains. These voids are not empty because something cleared them out, but because the long patient pull of gravity drew matter into the bright filaments around them, leaving these interiors progressively more open across billions of years, until what remained was the deepest silence the universe knows how to keep. And from this cold and spacious stillness, we turn now toward the worlds that drift through the dark with no sun at all, and toward what waits crushed in a perfect stillness deep inside the giants. Not every world that travels through the galaxy does so in the company of a warming star. Some planets drift entirely alone, cast out of the systems where they formed by the gravitational interference of larger neighbors during the crowded early ages of planetary assembly. They travel in permanent night, with no sunrise to mark the hours and no seasonal warmth to vary the long cold of their surfaces. The galaxy may hold as many of these wandering worlds as it holds stars, perhaps more, billions of dark planets, threading the immense spaces between the bright points of light we use to map the sky. Each one carries its own silence outward through the dark, a world complete in itself and answerable to nothing. Their surfaces sit near the coldest temperatures the surrounding space allows, frozen and still, lit only by the faint and scattered stars that make no real impression on the cold below. There is no day on such a world, no change of any kind that a clock or a calendar could track against the slow rotation of the seasons. Only the long and patient dark, extending in every direction without interruption, without end. And yet the image of these starless worlds as places of absolute cold and complete lifelessness is not the whole story, and the part that remains is unexpectedly warm. A planet carries heat of its own, left over from the energetic collisions of its formation and generated slowly by the decay of radioactive elements deep within its interior. On some rogue worlds, that internal warmth could be enough to keep water liquid far beneath a thick shell of ice covering the surface. The pressure of overlying ice and the steady heat rising from below could maintain a hidden ocean in permanent darkness, never touched by any life from outside, sealed away from the freezing vacuum above by a roof of frozen water kilometers deep. That ocean would be quiet beyond any description we have for quiet, undisturbed by weather or tides from a moon, warmed only from beneath, sitting still in the absolute dark. The idea that some of the most lightless places the galaxy contains might hold calm liquid seas, going about their slow chemistry in total isolation, is one of the more soothing thoughts this tour produces. Life, if it exists anywhere in that hidden dark, would know nothing of stars. Deep inside the giant planets, the extreme runs in the opposite direction entirely from the cold of those starless surfaces. The largest gas planets compress their interiors under pressures that ordinary experience has no frame of reference for, squeezing familiar substances into states that no surface chemistry ever produces. As you descend through such a planet's atmosphere, the gas thickens gradually rather than giving way to any solid ground, growing hotter and denser with every layer until the familiar rules governing gases simply stop describing what is there. Far below any level accessible from outside, the pressure becomes great enough to force hydrogen into a metallic state, a liquid that conducts electricity and flows in slow currents through the deep interior. Those currents generate the enormous magnetic fields that surround the largest planets, extending far out into space as invisible structures shaped by motion no instrument will ever directly observe. The very center of such a planet may reach pressures millions of times greater than the air pressing against any surface on this world, and temperatures that rival the outer layers of an ordinary star. In some of the giant planets, where carbon is present in the right layers at the right depths, the crushing pressure performs a transformation that feels almost too poetic to be planetary science. Carbon under that kind of compression takes on the crystalline arrangement we know as diamond, the same order geometry that makes a gem catch light on the surface of a small warm world. These crystals, denser than the surrounding material, would not stay suspended in the layers where they form, but would sink slowly downward, drifting toward the center on a journey measured not in days, but in ages. A slow and perfectly silent fall of crystal through layers of compressed matter that no eye has ever seen and no instrument will ever reach, going on for billions of years in the deep interior of a world orbiting a distant star. It is one of the quietest images on this entire tour. The most ordinary substance pressed by pressure into something rare, falling endlessly through the dark interior of a giant planet with the patience of something that has nowhere particular to be. There is a kind of peace in the image that has nothing to do with astronomy. All of the extremes we have visited on this tour, every dense remnant and fierce field and violent death and empty void, trace their origin to a single moment so far back in time that the distance is not really a distance at all but a boundary. Everything visible in the cosmos, every star and galaxy and quiet world and wandering remnant, was once gathered into a space smaller than the smallest thing you could hold between two fingers. The conditions at that moment exceeded every extreme we have described by margins so large that comparison becomes meaningless, temperatures beyond anything that has existed since, densities beyond the interior of any neutron star we will ever find. And then space itself began expanding outward at a rate that briefly exceeded any speed that light could match, carrying all of that compressed potential outward in every direction simultaneously. This was not matter exploding through empty space already waiting to receive it, but space itself growing, stretching the distances between every point and every other point in the same motion, so that no single location could be named as the center of what happened. Everything was the center, and everything was the edge at once. In the first fractions of a second after that beginning, the universe was too hot for any particle we would recognize from ordinary matter to hold itself together. The components that would eventually make up protons and neutrons moved freely through a sea of energy too dense and hot to permit anything as structured as an atom or even a nucleus. Only as the expansion cooled that sea did the first true particles condense from it, locking together into the simplest combinations physics allows. Within the first few minutes, the temperature had dropped far enough for protons and neutrons to assemble into the cores of the lightest elements, mostly hydrogen, with roughly 1 atom in 4 becoming helium, and only faint traces of anything heavier. That ratio, set in the opening minutes of everything, still describes the ordinary matter of a universe today wherever you measure it, in any direction across the entire observable sky. Everything more complex than helium would have to wait for stars to build it across billions of years, and then for those stars to die and scatter before any world like this one could assemble from the available ingredients. For a few 100,000 years after those first minutes, the universe was too crowded for light to travel freely through it. The young cosmos glowed with its own heat, but was opaque, a fog of charged particles through which no beam could pass without being absorbed and re-emitted almost immediately. Then the temperature fell below a threshold where electrons could settle permanently into orbit around nuclei, and the fog cleared all at once across the entire universe. The light that had been trapped in that fog was released into a suddenly transparent space and has been traveling ever since, cooling and stretching as the universe expanded around it, thinning from the fierce heat of its origin into the faint background warmth that fills all of space today. That ancient light is the oldest thing the sky contains, a record written in radiation of the moment the universe first became clear enough to see across. The tiny variations in its temperature from one direction to another carry the seeds of every structure that followed. The faint pattern of slightly denser and slightly thinner regions that gravity would spend billions of years drawing into galaxies and clusters and the long filaments of the cosmic web. Every atom of your body passed through that first fire. The hydrogen in the water, carried by your blood, was assembled in the opening minutes of the universe, forged when the cosmos itself was the furnace and everything that exists was still a single expanding heat. The heavier atoms came later, built in stars that lived and died before the sun ignited, scattered by explosions and gathered again by gravity into the cloud that eventually became this world and everything on it. You are not separate from the most extreme place on this tour. You're made of it, cooled and scattered and assembled across billions of years into something small enough to rest quietly in the dark of an ordinary night. The first fire spent itself long ago, and what it became includes everything you have ever touched and everything you will ever be. That is not a metaphor borrowed for comfort. It is the literal account of where the atoms in a human body come from, traced backward through stellar interiors and the opening minutes of time to a beginning that contained everything all at once. There is one final stop on this tour, and it is not a place in any physical sense, but a question sitting at the very edge of what physics currently knows how to answer. Empty space is not simply nothing. It has properties of its own, an underlying energy that determines the lowest state it can occupy, and the question of whether the universe's current state represents that absolute lowest resting condition or merely a stable intermediate one remains genuinely open. If space were resting somewhere above its true ground state, like a ball settled in a shallow depression with a deeper valley somewhere below it, then in principle it could settle further, the change spreading outward at the speed of light with no warning that could precede it. The details of this possibility are what make it dissolve as a source of concern rather than accumulate into one. A change that propagates at the speed of light can never send a signal ahead of itself, so there would be no approaching darkness to watch for, no gathering sign, no moment of awareness that anything was coming. The one catastrophe that requires no vigil is no catastrophe at all in any experiential sense. And the space we inhabit has held its present state through nearly 14 billion years of galaxies forming and stars igniting and worlds assembling without the smallest detectable deviation toward anything else. The long stability of the universe is not a background condition we happen to be experiencing by luck. It is the very ground on which everything else was built, the steady platform that allowed hydrogen to become stars and stars to become heavy elements and heavy elements to become worlds warm enough to hold liquid water and complexity for long enough that something small and aware could eventually open its eyes within it. The extremes we have visited tonight, every spinning remnant and fierce magnetic field and violent death and empty void and crushing interior and ancient fire, all of them contributed something to the calm world where you are resting now. The neutron stars are still turning in the dark. The black holes are still holding their silence. The voids are still keeping their immense and patient quiet. The ancient light from the first clearing of the cosmic fog is still traveling through the space above you as you lie still. None of it asks anything of this night. None of it reaches toward anything you love. The most extreme universe that has ever existed built, over long and patient ages, the most ordinary and sufficient thing, a quiet, dark, a steady ground, and enough warmth to rest in. If these slow journeys through the deep sky are the kind of company that helps a night settle and a mind grow still, then a like or a subscription helps others who might need the same thing find their way here. Sleep well, and good night.